So, good. So, we will continue our discussion on fluorescence spectroscopy, and today I want to focus on the solvent and environmental effect on fluorescence. That is the concept that we want to. Already you have seen some of those aspects, that solvent and environmental effect changes the separation between the two levels. That is what we had discussed. We will go little more detail. So, to recap what we had discussed, we discussed emission of light by a substance after absorbing on radiation, that we call it fluorescence. The emitted light has a longer wavelength or lower energy, right, because it is going from say S0 to S1 to any vibration state, but while it is coming, it comes from S1 V0 to the ground state. So, it has a lower energy, higher wavelength, right. It differs from phosphorescence, because phosphorescence the radiation come from triplet state, not from the singlet state. So, typically it is a longer time, right. So, phosphorescence has a longer time, and emission is like differs from fluorescence, because emission stops when the excitation stops, right. So, that means you are exciting and it is coming back, but if you do not excite, nothing comes back. So, that is a fluorescent dye or biological fluorophore, those are example of fluorescent molecules. Now, here the molecule absorbs light, electron gets excited, emits while returning to the ground, these are the concepts, and the shift that happens because of longer wavelength is called Stokes shift, and it is typically explained very well by something called Jablonski diagram. So, these concepts we already had looked at, the time scale and all those already we have looked at. How we do these experiment, that also we have looked at, but again I will revise it. Instrument called fluorimeter, it measures the fluorescence, measures the intensity versus wavelength distribution. What is the unit of intensity? Anyone that you measure on y axis? Arbitrary unit, yes, lux you can measure it, but generally you put it in arbitrary unit. The y axis is arbitrary unit. What is on x axis? Is wavelength. Wavelength is measured in lambda nanometer, right. So, it is a nanometer versus arbitrary unit. That is a wavelength distribution of fluorescence, the emitted photons, you measure it, and that is measured by photodetector. So, it depends upon the sensitivity of the photodetector, what is how many photons you can detect it and how many it is emitted. So, typically you put in arbitrary unit, right. So, and it is helpful in determining the molecular structure, the dynamics, the concentration, the environment effect and all those. The basic principle remains same, a light source upon excitation. So, light source can be like a laser based light or a like a long variation wavelength like a xenon lamp, mercury lamp, all of these can be used as a light source for excitation. Your sample is sitting somewhere in sample chamber, typically it is kept in a quartz cuvette, light has to pass through it. So, here is my light that is passing through it, right, and then light is coming, you have an emission monochromator and you put it to photodetector. So, sample can absorb and emit fluorescence, that is the basic concept we are capturing in this spectrophlorimeter, right. So, now today that the concept that I want to touch upon, the solvent and environmental effect, how solvent and environment of the substance can play an important role and where we can use such concepts using the basic concepts of fluorescence, right. So, fluorescence as we know it is a emission of light that we are measuring, right, emission of light that we are measuring, and this emission coming after the substance has absorbed the energy. So, that is excitation. Absorption is excitation and what we are measuring is emission of light. It can happen any substance, whether it is organic, inorganic, the materials and all those can show the behavior of a fluorescence, right, and it is a highly sensitive to environment in which this substance is. Why environment matters? Because fluorescence is not a fixed phenomena. it changes depending upon surrounding. And the basic concept that we already discussed, suppose this is the energy gap between the lower state and higher state, it can change depending upon what is nearby, what is in the solvent, what is in the surrounding. So, this change actually enables us to probe the chemical environment of a fluorophore, right. So, and it can be also used, if this is so sensitive to the chemical environment, that means we can use this concept in sensing, in diagnostic, sensing something like where it is sitting, and diagnostic, of course, diagnostic you can make a probe based on the fluorescence for diagnosing anything, and many things are based on the fluorescence diagnostic. Some of those probably we can look at as we go forward, right. So, local environment, which we can call it micro environment, and one example I already gave you, a tryptophan sitting in the protein in a loop, whether it is facing solvent or facing interior, can have different micro environment, right. If it is facing interior like this, it is surrounded by hydrophobic amino acids, right. When it is exposed like this, it is surrounded by water molecule. So, environment of that tryptophan, which is a fluorophore, is changing whether it is buried inside or exposed, and therefore, the fluorescence intensity, also the wavelength, emission wavelength changes, right. So, that has an effect. What it changes? The intensity changes, the wavelength changes, and also the quantum yield changes. You remember what was quantum yield? The ratio of the radiative photon, like a radiative photons that is coming, divided by total radiative plus non-radiative photon, that is a quantum yield. How efficient is a probe that is measured by quantum yield of a probe, right. So, that is the efficiency. So, if you increase temperature, or if you have a quencher does what? It takes the photon, whatever should come from radiative, it makes it non-radiative. So, if there is a quencher like a dissolved oxygen or something like iodine, it decreases the fluorescence intensity as a non-radiative deactivation pathway, deactivating it, just taking the productive radiation to non-productive pathway without giving any signal. If there is a high viscosity or structural rigidity, it can enhance the quantum yield by restricting the molecular motion. If tryptophan is not doing like this, or any molecule, fluorescent molecule, if it is in rigid, probably it will change the fluorescence intensity. So, intensity can change depending upon what is quencher. Quencher is a substance that quenches the or reduces the fluorescence efficiency, right. So, one example that I gave you, you remember my protein had a two domain, one tryptophan was in one domain, another tryptophan was in another domain, and using this quenching experiment, we can probe what is the local environment of that tryptophan, right. So, those are the use of the experiments that we are doing. The another environmental effect on the fluorescence can be seen by shift in the emission spectra. So, emission spectra, that is a Stokes shift. So, polarity of a solvent. Now, just one thing that I forgot to mention, you remember what is written, presence of a quencher like dissolved oxygen. Where do you have this dissolved oxygen present during your experiment? Do you remember or do you know? Anywhere, buffer बनाते हो उसमें पता नहीं पानी dissolve है, right? होता है या नहीं पानी में, वाटर में there is a dissolved oxygen or not? होता है ना, मछली सांस तो वैसे ही लेती है, dissolved oxygen they consume. So, if you want to remove that dissolved oxygen, what kind of experiment or experimental carefulness you should have, what kind of precaution you should take? I want to remove this dissolved oxygen from my sample. I prepared a buffer and I want to do this experiment based on fluorescence. I know that dissolved oxygen could be a problem. So, what should I do? Nitrogen say you purge it. So, you have a buffer, pass the nitrogen to this. So, what will happen? Oxygen will go and it makes the inert environment. So, all the inert environment can be obtained by just purging with nitrogen, and then you have reduced the chance of dissolved oxygen and therefore quencher. So, these are some of the practical consideration you need to do when you are doing experiment using fluorescence. How carefully you should make your buffer where you are doing experiment, you should get rid of quencher, otherwise you do not know what is the effect of quencher coming without your knowledge, it can reduce the fluorescence efficiency. Okay. So, the another important point, polarity of a solvent, in which solvent you have to do experiment, that is also very important because that has a effect on microenvironment. It influences the spectral shift, right. So, excitation and emission wavelength it shifts, and if the solvent is polar, larger shift may be happen due to destabilization of excited state. So, you concept is extremely similar. This is my difference between ground state and excited state. Depending upon polarity of the solvent, this can go like this or it can happen like this, right. So, what I want? Always want this, right. I always want this. So, you have to change the polarity of the solvent. If it is more polar, separation can be increased. Therefore, selecting a right kind of solvent is extremely important to do the experiment. First of all, your protein has to be happy in that environment. Second, it should be polar enough to give you the signal. Now, another important concept or consideration that you have to have, there is possibility of internal charge transfer, right. So, the local environment as we are discussing, it has a significant effect on the fluorescence intensity, and there is a intramolecular charge transfer can happen by influencing the excited state. So, all the energy has to come from excited state. If something is there which takes away the energy, it will affect. So, that's excited state level can change, and it can change through the non-radiative decay pathway. So, internal charge transfer is not preferred one. Similarly, proton transfer and excited state reaction is not. So, if you remember, I discussed two kind of quenching. What were those? Static quenching, dynamic quenching. In one of the quenching, your excited state was interacting with your quencher and transferring the energy. If that is happening, your intensity and efficiency will go down. So, you do not want your excited state to interact and lose out the energy to the quencher, right. The another important aspects, and therefore, I often told you something, I will remind you what I have told. So, probe-probe interaction. Probe-probe interaction means fluorescent probe we are talking about. Probe-probe interaction should not happen. Therefore, you remember I told कि अगर एक ट्रिप्टोफैन प्रोटीन में है तो बहुत ही अच्छा है, एक से ज़्यादा है तो problematic है. So, the experiment that I discussed with you of this protein which was 2 domain, both domain has a 2 tryptophan. For experimental design what we had done? Mutated one to leucine at one time. So, I had only one tryptophan from entire protein which is reporting its microenvironment, mutated the other one. So, this probe-probe interaction, right, changes the local environment. So, if these tryptophan are coming closer and they are talking to each other, that is also not good. If the 2 tryptophan is giving this signal, you do not know signal is coming from where. So, I do not want that. I just simply want it a cleaner system where the signal is coming from one tryptophan, right. So, that affects the probe-probe interaction, changes the polarity, viscosity, pH, ion concentration, so many of such things. So, interactions alters the probe photophysical property or physiochemical property, and including the emission spectra becomes either lower or too complicated to interpret. Wavelength can change and quantum field can change. Therefore, typically you do not want anything to interfere with your signal which is coming from a particular probe, and you want a cleaner system. The another important conformation is probe conformational change. Fluorescent is giving you signal. Suppose this guy is too much wobbling or something happening, it is a decay. You remember we have talked about something called fluorescence life time. So, it should conformational change can dictate the intensity that comes. So, if the fluorescence lifetime is too short, it can have an impact. So, that also the probe conformational change in the micro environment can change the quantum yield and provides, like, it changes the quantum yield. Therefore, you can use in a good way to look at which is decaying faster, which is decaying slower, and you know the location of that probe in the particular environment. So, rigidity changes, right, rigidity again gives you the local environment. So, increased rigidity of fluorophore generally leads to increase in fluorescence intensity, and then the other way, if it is flexible, the intensity will be lower. This is called, this effect is called is rigidochromic effect. Rigido means like it is becoming rigid, chrome means light, chromic effect, that is a fluorescence. So, all the time we want to increase the efficiency of a fluorescent probe, right. We want, like, want to use less and less sample. Why? Let us talk some economics of a fluorescence. You are employed by a company, since you have done the biophysics course and molecular biophysics course, and you became expert in fluorescence, and they wanted you to come up with an idea where company has to invest less, right. Let me, if you want, I will also give you an example. Suppose you are hired by this Mankind Pharma, which makes the pregnancy kit, okay, and you have to come up with a fluorescent strip for detecting the pregnancy. Abhi unka hai na, right, they have a, they are market leader in pregnancy kit, Prega News. All the time when you go to airport or some film actresses doing advertisement of that Prega News. So, they are a market leader in pregnancy kit, and they want to even beat their competitor by providing superior quality fluorescence, and they now want to come up using similar concept to make a fluorescence detection kit. What your objective is going to be? Since they have hired you, invested in you, they want something magnificent from you. So, you essentially you start with a basic principle, can I increase the quantum yield of my fluorophore, right. How it helps? If you increase the quantum yield, you require less fluorescent molecule to be used in this strip. So, you have significantly reduced the cost of the development, right. So, if this kit can be made in 10 rupees and you price for selling it to 90 rupees, 80 rupees ka munafa, suddha bachat, right. But if your cost of development is 60 rupees and you are selling at 90 rupees, the company do not want that. They want less investment in a superior technology where profit margin is more, right. So, you have to always think that how you can suppress the non-radiative decay, because that is a taking away the energy. So, you have to design in a fluid or non-rigid environment like a solution where you can increase the quantum yield of the product, right. That is how your design should come. Non-radiative pathway, whatever is not in your control, you cannot do much about it, but you can do whatever, wherever the basic concepts will help you to increase the quantum yield. Similarly, enhancement of radiative decay you have to. So, you rigid environment provide that physically restrict this intermolecular motion and conformational change that might be happening from the sensor, or shut down the non-radiative pathway, increase the radiative pathway, and that is how you increase the quantum yield of that. Now, another important aspects that you can think of is the solvent purity. Remember, if something is present, I gave you one example, because all the protein will like to have in some solvent, right. If you are making your solution in a buffer where there is a dissolved oxygen, will that be helpful? No. So, you have to come up with a pure solvent where energy level are not perturbed by the solvent dissolved whatever is there, iodide, bromide, oxygen, all should be pure. So, if it is doing it, if there is effect of solvent, that is called solvatochromic effect. The guidelines choose a solvent that matches the polarity requirement of your fluorophore. Like if your fluorophore is non-fluorescent, non-polar, you have to choose a non-polar solvent like hexane. If your fluorophore is there, choose a polar solvent like ethanol or water. That is the, because you can dissolve more and you have to have a pure solvent done. If it is something in between, you have to make a mixture to have it happy. The solvent purity is important. Impurity can quench the fluorophore, introduce the background signal which you really do not want. So, your guideline is use high purity spectroscopy grade solvent to minimize the contamination and the scattering. Where are you going to buy this? High purity spectroscopic grade solvent. Where are you going to purchase this? Do you think anybody makes this kind of solvent? So, when you buy, go and check it the website of any chemical company that makes some of the solvent, they have LR grade, AR grade, high purity grade. जितना अच्छा grade उतना ज़्यादा पैसा. So, AR grade or spectroscopic grade solvent, many times you have to purchase it. You invest in this in getting a good solvent, but that helps in a longer run. Okay. Now, another important aspect is absorption and transparency. So, solvent should not absorb. We want to probe fluorophore, not the solvent. So, we have to have a background minimally interfering or no interfering with the fluorophore. Solvent should not absorb the excitation or emission wavelength. Check in the UV visible spectroscopy that it is not absorbing where we are using excitation wavelength. So, these are some of the practical consideration. Okay. Now, viscosity, right. We talked about viscosity is important, rigid environment or flexible environment. High viscosity can reduce the non-radiative relaxation and increase the fluorescence lifetime. So, guideline for studying the involving rotational dynamics, where we are want to understand the rotational dynamics of a fluorophore, or lifetime measurement, you can consider the solvent viscosity. You do not want things to decay before you can detect it. So, you can little bit rigidify it by putting the solvent. pH and chemical stability is extremely important, right. pH can alter the ionization state, many of the fluorescence is there. You remember the ionization state of an amino acid? What, like if you remember pKa, pK1, pK2, pK3, tryptophan, what pH should I avoid? 10 के आसपास. So, high pH I should avoid, right. Similarly, histidine is not a fluorophore, but अगर histidine अगल बगल में है tryptophan के, what pH I should avoid for histidine? 6, 7, right. So, this changes the ionization not directly for fluorophore, but even the micro environment it can change. So, you have to be really careful while doing this experiment that the solvent, the pH, the chemical stability has to be. So, use buffer solution for pH sensitivity. Therefore, protein is always used in a buffer. What is the use of buffer? pH के shock को कम करेगा, right. That's a use of buffer. Solvent, the solvent temperature influence the molecular motion, fluorescence intensity. So, always do the experiment in a controlled temperature. Now, I was saying fluorescence is like not that expensive, but if you start adding all of these things, control, it can be done with a Peltier based control, temperature control. So, that add up the cost for a fluorescence, but that helps you in detecting or getting the more signal. So, in fluorescence spectroscopy, the choice of solvent is critical, extremely critical, as we see it is changing the efficiency, the mobility and all those, significantly influence the fluorescence intensity, its a wavelength, overall spectral characteristic. Therefore, you have to take care of your polarity of a solvent, purity of a solvent, absorption and transparency, your solvent should not absorb, the viscosity has to be taken care because that changes the fluorescence intensity, pH and chemical effect, and solvent relaxation and Stokes shift basically can change it. So, whatever causes energy loss is not good because that can cause the larger Stokes shift, right. So, you want to avoid all of these external factors that are there, and essentially what it does, fluorophore, if there is a solvent, less polar solvent or effect, it reduces the energy. So, therefore, you can see the effect of the solvent on fluorescence emission spectra. So, typically fluorophore has a larger dipole moment in the excited state than the ground state. Solvent shift the emission to a lower wavelength due to stabilization of excited state by interacting with a polar solvent, and solvent polarity increase, this effect becomes the larger. So, essentially solvent plays an extremely important role to give you the real example of a molecule called prodan. It is a emission spectra based on the heptane and water. If you change from heptane to water, right, increase in the polarity water, it changes the emission wavelength. It is going from 350 all the way to 650. So, that is the effect of a solvent and its polarity. You see, emission intensity is not changing, but wavelength is changing, right. Another effect that we discussed already, the temperature. If you change this, so here is a fluorophore 100 K and 300 K, the same prodan in different solvent, your emission spectra changes depending upon what is the temperature, right. So, temperature, solvent and all those changes. So, decrease in temperature, increase in viscosity and increase in fluorescence contribution to non-relaxation state, therefore, you have a blue shift, right. So, polarity, red shift, temperature, blue shift. These are some of the effects. So, all of these that we discussed is called solvatochromic effect. Solvatochromic effect. It is a phenomena where molecule color or fluorescence changes depend upon solvents what is present, right. This effect is crucial for fluorescence in probing the molecular motion, the molecular environment, the relaxation property and all those, right. So, low polarity solvent and high polarity solvent, it can lead to the low polarity, it is a blue emission, and high polarity excited state is stabilized, smaller gap, therefore, red shift. So, this represents the positive solvatochromic effect, and for negative solvatochromic effect your ground state should be stabilized, right. So, that is called solvatochromic effect. It depends upon the solvent and therefore, so some of the fluorophore how do they behave, that I will take it, but before I go here just stop for a moment and take any question that you may have, right. So, two kind of this effect of solvatochromic effect, positive and negative. So, absorption emission band shift to a longer wavelength means red shift. The solvent polarity is increasing. We had seen for this paradon from a non-polar solvent to polar solvent, there is a red shift. So, what happens? The excited state is more stabilized than the more stabilized by this polar solvent than ground state. One example of this, say coumarine, it is a dye in non-polar solvent like hexane, emission is in the blue, and polar solvent like ethanol, emission is towards green or yellow. Nile red is another fluorescent molecule, shows a strong red shift in a polar solvent, right. That is a positive solvatochromic effect. Now, use this concept of two dye that I give you, what kind of sensor you can make it. You have to think what we are teaching you in a real life scenario where you can use this concept. Can you use this concept of shift in the emission wavelength somewhere for sensor, for detection, for something? Okay. Let me give you some hint and you can think of. Let us think a thought experiment. अभी सेल में नहीं करना है, just simple. Now, let us see, you are very passionate about cancer biology. All of you are, many of you are for cancer biology. I want you to design experiment that you have studied, right. I do not want you to do a fancy experiment. Design an extremely simple experiment related to cancer biology, where you can look at the tissue that is cancerous versus tissue that is normal. अब इसके लिए स्पेक्ट्रोस्कोपी का concept remains same, but you have to know the tissue behavior. Can you give an experimental setup based on the concept that we are discussing? What changes between non-cancerous tissue and cancerous tissue, normal tissue versus cancerous tissue. उसके बाद क्या होता है? pH can change. Okay, great. What else? pH becomes acidic. Wonderful. So polarity is pH is changing, that means polarity and all those can change. What else? In terms of physical property of the tissue, वो तो हाँ ठीक है, डिवाइड रेपिड, लेकिन वो रैपिडली डिवाइड होने के बाद होता क्या है टिश्यू? इट टेक्स मोर ग्लूकोज, दैट्स फाइन, एंड देयरफॉर द इफेक्ट दैट इज reducing the pH, which is called Warburg effect, right? All of you have studied, lower the pH. So pH understood. In terms of rigidity, rigidity increases. So two concept now you learned: rigidity increases, pH decreases. Can you use this as a sensor? Thought experiment. I am not asking you to inject in somebody's body and do it, right? But can you think of some experiment of, because polarity is changing and rigidity is changing, your fluorescence signal can change. So similar kind of concept can be used, although you for a human test you have to do it a advanced one, but extremely these kind of simple experiment can be thought of making a sensor which probably may or may not exist, but at least you can propose some kind of this thought. So when you go for a job, you do not ask job, you propose that what you can bring it on the table for a company to do. If you come up with a proactive approach, you will be always desired, right, because this guy thinks and has a attitude to do something. Coming back to negative solvatochromic effect, what happens here? There was excited state getting destabilized, here ground state gets stabilized. So here occurs when ground state is more stabilized than excited state in a polar solvent. For an example, nitroaniline exhibits blue polar shift because its ground state is highly stabilized by hydrogen bonding. So this again can be used in enzyme kinetics and all those this kind of concept of. So why it is happening? Because solvent molecule is interacting with the solute via dipole-dipole interaction. In one case it was excited state getting stabilized, in another case it is a ground state getting destabilized. Interaction happening between the solvent and your fluorophore, these two states by various forces, hydrogen bonding it can have, the dispersion force can have, the dipole interaction can have, and practical application like a dial like Nile red and this Ricard dye used to measure the solvent polarity, right. Environmental sensing you can use it. So fluorescence can detect polarity in the biological membrane and microenvironment of the tissue that I was talking 2 minutes back. This Ricard dye shows the dramatic color change across the solvent due to solvatochromic effect. Fluorescein sodium is another dye, exhibits this solvatochromic fluorescence in biomedical application, right, or a semi aromatic imide compound. It can emit the full color fluorescence depending upon what is the solvent polarity. So it has a extremely important application in biomedical, environmental sensing, the solvent polarity sensing and all those. It is a extremely useful technique for many of the applications. So already we discussed senses the pH. So fluorescence can be used as a pH indicator. Right. There are some molecules which are sensitive to pH, some molecules which are sensitive to pH, and due to equilibrium between protonated and deprotonated form of fluorophore, it can differ the fluorescence spectra, and it can measure the pH inside the cell. Coming back to whatever he gave, cancer cell dividing rapidly, consuming glucose, not taking it to 2-CA cycle, just ending at lactate, pH drops. pH drops drastically from whatever 6, 7 pH to pH 2, 3. pH is dropping, and therefore you can use some of these fluorescent dye to sense those cells where pH has dropped. And one can, like I have here is a ratiometric pH of this neuron, and you can have the pH dependent excitation and emission curve to find it out how the wavelength is changing. So, it is a good example for sensing. So, what we can conclude, the solvent has a effect, the environmental has a effect on pH emission. So, solvent and environment profoundly affect the fluorescence, and that enables us for like a sensitive detection of molecular, like a molecular changes that will be happening. It can change the local environment of a tissue and cell, and it has profound application in biomedical, right. You can design a fluorescence based assay for monitoring the reaction, for tissue application, many other things. It has a profound application that you may have. Okay, so that was all about the solvent and environmental effect on fluorescence and its possible application that you may think of, where we are going to use this extremely simple fluorescence based experiment and its impact because of the local environment, because of solvent, because of polarity and all those. Okay.